Good evening, all of you. Welcome back after the Pongal vacation. So, is the audio clear and the video also? Tell me. Is it clear to all? Since I got a sore throat, so if you have any problem, please forgive me. Let us continue for the today's session. In the previous class, we discussed the concept of maximal ideals and prime ideals and problems based on that. So, do you have any queries on the previous class session for anybody? Please tell. So, first we clarify our doubts, then we go with our class session. If clear, then I will start the class session as usual. Any queries to anyone? Yes or no? Right. All right. Then let us begin our today's session. So, please take a note of this question. In a Boolean ring R, every prime ideal P not equal to R is maximal. It is also one of the previous year questions. So please take a note of this. Then we discuss with the approach how to prove it. After noting, please tell. So as per the data, you take the Boolean ring R. So R is nothing but the Boolean ring. So can you tell the special property of R? What it is meant by Boolean ring? The special property of Boolean ring. When we call a ring as Boolean, right? So A square equal to A for all A belongs to R. In other words, every element is idempotent element in the ring. And it is also given that you consider an ideal which is prime ideal. So you take that P not equal to R is a prime ideal. So immediately you can visualize the content as this is the ring R and this is the ideal P. And P is not equal to R, and it is also given that P is a prime ideal. So as per the question considered, you have to show that P is maximal. So as per the question task considered, we have to show that P is maximal. So it means that there is no other ideal of R which is bigger than P and smaller than R. So generally, the usual technique we follow to show that P is maximal is if you take that any ideal I such that P is proper subset of I and I is subset of R. So if you prove that I is equal to R, then automatically, as per the definition, P becomes maximal. Do you accept it? Say yes or no. Right. So this is our hypothesis, what we considered. So I have taken that I is any other ideal of R such that P is a proper subset of I and I is subset of R. So from this we can say that there is an element in I which is not in P. So you can say there exists an element X belongs to I such that X is not in P. Since the ring is Boolean, whatever the element you consider, this property holds. So you can write that X square equal to X. So please understand that whatever the property you are proving in abstract algebra, that is applicable for every type of structure. So you are dealing with numbers, polynomials, matrices, everything you are taking. So X square is equal to X that you have taken here. Now you take any other element in the ring. Now what happens? Multiply this equation both sides with y. So you have that x square y is equal to xy. Taking this value to the left hand side, x square y minus xy is equal to 0. So what this 0 means? This is the 0 element of the ring. So every ideal by default contains the 0 element. So this value belongs to P. Accepted? Right. So if you consider this thing, this implies x into xy minus y equal to 0, taking x as common. Now see, this is the product of two values and this value belongs to P. As you have taken that, it is a prime ideal. From the definition of prime ideal, whenever the product belongs to the ideal, one of the elements must belong to that ideal. That is the definition of prime. So in this product, either x belongs to P or xy minus y should belong to P. Since x does not belong to P, so the only possibility is xy minus y belongs to P, since it is the prime ideal. Do you accept it? Say, any questions to anyone? Please tell. Right. Now, so what is means? Xy is an element, y is an element, the difference is belonging to P. That means if you calculate the value of xy minus y, it is an element in P. So let us give the result a name. So let us take that xy minus y is equal to B and this value belongs to P. So from this you can say that y is equal to xy minus B. Accepted? Right. Now here we use the property of ideals. So here you have taken that B is an element in P here. Since I is the bigger set than P, B also belongs to I. Another thing is, you have taken the property like this. This is I, this is the ring R. You have taken that Y is any element in the ring, X is an element in I. From ideal definition, XY belongs to I. So, I contains two elements, XY as well as B. So, from the definition of ideal first condition, XY minus B belongs to I. Therefore, Y belongs to I. Therefore, R subset of I. Clear? Any questions? Please check the diagram and conclude yourself. If you have any other queries, I will discuss. Please take a note of that. Any questions or any doubts for anybody? Are you clear? Right. So we have I is equal to R. Hence, by definition, P is the maximum ideal of R. That's it. That is the solution of the problem. So after noting, please tell, I want to discuss the other thing. After noting, please tell. Right. Can I erase this? Fine. The next question is, you consider the ring R power C. Here, C stands for the continuous functions. So I have considered all the continuous functions from closed interval 0, 1 to R. So R power C is a ring which contains all the continuous functions from closed interval 0, 1 to R, and here R stands for real valued. So I am taking all real valued continuous functions from closed interval 0, 1 to R in a set, and it is a ring. And I have taken a new set that M set of all the functions in the ring such that for those functions 1 by 2 is the root, and you take another function that it is the linear polynomial x minus 1 by 2. Now the question is, the set M is generated by G. This is the claim of the problem. It is also a previous year question. Now please look at the statement. I am considering all the continuous real valued functions from this interval to R in a ring. That ring is denoted with the symbol R power C. So here addition and multiplication is nothing but addition of functions and multiplication of functions. F plus G, F dot G, the usual thing. And in the whole set, I am taking the subset M such that it contains those functions for which 1 by 2 is a root. So this is our imaginative picture. This is the whole ring R power C in which I have taken M for which the function root is half. Now we have to show that this set is generated by the function G, where G is denoted by G of x is equal to x minus 1 by 2. That we have to show. Clear? Yes or no? Right. Now, from the very definition of G, can we say that this function belongs to M or not? From the very definition of G, right? So, we know that, let us say M is an ideal. You consider all the multiples of G. It is also an ideal. So here, since G is a part of M, so generated by G is also a subset of M. So if you want to show that these two sets are equal, it is our responsibility to show that M subset of generated by G. This thing we have to show. Now, how can we show this? If you take any function here, we have to prove that any function in M can be represented as a multiple of G. So what happens? Whatever the function f you take in M, it must be represented as G into something. So automatically what happens? If you are able to write f like this, f will belong to this set. Therefore, M is a subset of G. Hence, the claim will be proved. Are you clear with the ideology? Please tell. If we are able to show that every element f belongs to M can be represented as f is equal to G into something. So it means that f belongs to generated by G. So automatically M is a subset of generated by G will hold, so that both will be equal. Accepted all. Right. So it is our responsibility to show that f is equal to G into something. So what it is, you have to build a continuous function such that f can be represented as product of this. So here, let us give a name for it. Let us say f is equal to G into h. So what this h will be? Now here, I am going to define the function as h of x is equal to f of x divided by g of x if x is not equal to half, f of x if x equal to half. Are you clear now? In this way, I am defining the function, because if you consider g of x into h of x, if you consider this value, here you got two possibilities. In the closed interval 0, 1, you can take any x. You can take any x in this interval. So you are taking from 0 to 1 all values. So x may assume the value 1 by 2 also. So typically the possibility is you will consider the value x not equal to 1 by 2 and you will consider the value x is equal to 1 by 2. So what happens if you consider g of x into h of x here? It is nothing but g of x into f of x by g of x. Both gets cancelled, you will get f of x. If you take that x is equal to 1 by 2, then g of x into h of x is nothing but g of 1 by 2 into f of 1 by 2. This is 0. Also, at x is equal to 1 by 2, f of 1 by 2 is 0. This is a 0 function, this is a 0 function. The value is, because f of 1 by 2 is nothing but 0 here. So you have two things. So whatever the way you consider, g into h is giving f for us. Therefore, every element f belongs to m can be represented as g into something. This something is defined like this. Therefore, m will become a subset of g. Hence, m is generated by g will hold. That is the solution of the problem. Please check that. Please take a note of this. Any questions, any doubts for anybody? Right? And another thing is, the ideal m, what you have taken, will become the maximal ideal. So let us prove this by doing some topics like homomorphism of rings. Then again we come back to the concept of maximal ideals. So let us start with the concept that homomorphism of rings. Let us discuss on this. So if you know the content of homomorphism with regard to group theory, then homomorphism of ring theory is very similar and you will have to prove problems on it. So just go back to the concept of homomorphism in group theory once again. So in group theory, how do we define homomorphism? If you take two groups G and G dash, we consider a function f which is defined based on the structure in the groups you have chosen, and f must satisfy the condition that f of AB is equal to f of A dot f of B. Generally we assume that G comma dot is a group, G dash comma dot is a group. This is the pattern. Or if you take that G comma plus is a group, G dash comma dot is a group, then you have to verify the condition that f of a plus b is equal to f of a dot f of b. So this is the one single condition we verify between the two groups based on a function. If the function satisfies this condition, we say that it is a homomorphism on the groups. Clear to all? I think you have remembered the definition of homomorphism. Say yes or no. Now, coming to the concept of rings, if you take that f from R to R dash is a function between two rings, then here f must satisfy two conditions. Because in group, you are dealing with only one binary operation. In rings, you have two operations, addition as well as multiplication. So the first condition is based on addition, that f of a plus b is equal to f of a plus f of b. And second condition, f of a dot b is equal to f of a dot f of b. So if f satisfies these two conditions, we say that it is a ring homomorphism. Now you can see the difference between these two, how we define in groups and how we define in rings. Here both sides plus will come. Here on the LHS side, plus is the addition which is defined on the domain ring. On the right hand side, plus is nothing but the addition which is defined on the codomain ring. So here symbols will not vary, their actual meaning will vary. So here f has to satisfy two properties, then only we say that it is a homomorphism between the rings R and R dash. Okay? Are you clear to all? You please take a note of the definition. And one fundamental thing is always identity is paired with identity. Always f of 0 is equal to 0 dash. Here 0 is additive identity. So additive identity is paired with additive identity only. Right? Now, if you remember the properties of homomorphism in group theory, same properties will come here. So, in group theory, we define kernel as, here kernel F, we define it as set of all x belongs to G such that f of x is equal to E dash. In rings, we define the kernel as set of all x belongs to R such that f of x is equal to 0 dash. Now, can you observe the difference? The definition is very similar. So, multiplicative inverse, so you are saying that f of a inverse is equal to f of a whole inverse. Those things will come automatically. The same properties will come here. So, here we just check for one condition, there we check for two conditions, that's all. The basic properties of homomorphism will hold automatically here. There is no need to prove them separately. You just remember the properties of homomorphism of group theory, what you learned. Those things will be applicable here as it is, without any change. Okay? Right. Now, observe the difference between these two. This is the kernel definition in group theory, and that is the kernel definition in ring theory. So, if you know the definition of one, automatically you are able to write the other. Do you accept it? Say. Now, can you tell that what is the significance of kernel F with regard to G in groups? Please tell. Kernel F will become what for G? Any one of you. So there we proved that kernel F is a normal subgroup of G. Accepted? So here kernel F is an ideal of R. So in the domain R, kernel F is an ideal. And one more result is, there you proved that F is 1, 1 if and only if kernel F equal to singleton E. Can you recollect this property of groups in homomorphism? Same property will come here as it is. So again we prove that F is 1, 1 if and only if kernel F is equal to singleton 0. Now you see the difference. Here we prove the result with identity E. Here we write the result with identity 0. Very similar result. The proof is also very similar. We are going to prove it right now in today's class. And another thing, we have proved one interesting property, that fundamental theorem of homomorphism. So there we proved that if F is a homomorphism between the two groups, then G by kernel F is isomorphic to F of G or G dash sometimes. Here also the same fundamental theorem will come. R by kernel F is isomorphic to F of R, the homomorphic image. So if you talk of words, there literally we write that every homomorphic image of a ring, of a group, is isomorphic to some quotient group. This is the statement you have written in group theory. Every homomorphic image of a group is isomorphic to some quotient group. The same statement will follow here. Every homomorphic image of a ring is isomorphic to some quotient ring. If you just replace the word group with ring, the same statement will come for the fundamental theorem of ring homomorphism. And the proof is also very similar. The same steps of proofs we follow here. So that is the beauty of abstract algebra. If you are done with group theory correctly, then the same thing you can do with ring theory in a very easy manner. Okay? Now, the other thing is, we have discussed some other definitions in group theory homomorphism, like monomorphism, epimorphism, isomorphism, automorphism, endomorphism. I think you can recollect the technical words of homomorphism. Can you? These words are familiar to you, right? The same definitions will come here. Without any change of the word, the same will come. So, if you take that F from R to R dash is a homomorphism, if the function is 1, 1, we call it as monomorphism. If the function is onto, we call it as epimorphism. If the function is a bijection, we call it as isomorphism. So the same definitions will come again. The only definition is there, the only change is, there we write F from G to G dash. Here we write F from R to R dash. Same definition, same pattern, no change in the technical verbatim. Okay? I think it is not necessary for you to repeat the definitions one more time. I think you can grab the idea. Is it necessary for you to tell again what is monomorphism, epimorphism, isomorphism, etc.? Now, let us start with the things what we discussed just now. We are going to prove them in an easy manner. So the first thing is, you take that f from R to R dash is a homomorphism. So the first thing I wish to prove is kernel F is an ideal of R. So what is the pattern to show this result? First we have to show that kernel F is a non-empty set. Then we have to show that the two conditions of ideal will hold in the kernel. So first you write the definition of kernel. It is a set of all elements in the domain ring R such that f of x is equal to 0 in the codomain. So as we know that always f of 0 is equal to 0 dash. Image of 0 is 0 always. So 0 belongs to kernel F. Therefore, kernel F is a non-empty set. That was the first one. And let us take two elements. Let x and y belongs to the kernel. So from the very definition of kernel, you can say that f of x is equal to 0 dash and f of y equal to 0 dash. Now we have to show that whenever you take two elements in the kernel, as per the first condition of ideal, we have to show that x minus y also belong to the kernel. So what does kernel means actually? We take those elements whose image is 0. So if you want to show that x minus y should belong to the kernel, so we have to prove that the image of x minus y is 0. So for this, you consider that f of x minus y, since f is a homomorphism, you can write it as f of x minus f of y. So this is nothing but therefore x minus y belongs to the kernel. You please take a note of this. Any questions you can ask. After noting, please inform. Any questions, any doubts for anybody? Right. Now, for second condition, what we have to prove? If you take one element here, one element in the ring, the product should belong to the kernel. So if I take an element A here, if I take an element R in the ring, the product RA as well as AR should belong to the kernel. So that kernel satisfies the second condition of the ideal, hence the result will be proved. So for this, you consider that R is any element in the ring, A is an element in the kernel. So immediately you can say that f of A equal to 0 dash. Now you consider the value of f of RA. Since f is a homomorphism, this will be written as f of r dot f of a equal to f of r dot 0 dash. Since 0 into anything is 0, it is nothing but 0. So RA is an element. To this you have applied f, the result is 0. So from the very definition, RA belongs to the kernel. In the same manner, you can prove that AR also belongs to the kernel. Therefore, it is an ideal. That is the proof. So if you just understood the definition, it is very easy to prove the problem. Okay? Please take a note of that. Then we randomly discuss a small problem. After noting, please tell. Any questions for anybody? Shall I proceed? Right. So let us take a small problem that so you consider the ring Z of root 2. So how is defined? We take the elements of the form m plus n root 2 such that m comma n are integers. So this is a ring. Similar kind of problem you have done already, that q of root 2 is a field earlier, where we define the elements in a similar pattern. Can you recollect the idea? How we have proved that in the beginning of ring theory, q of root 2 is a ring, say. So I want to define a function from z of root 2 to z of root 2 on the same set. I am defining. So how I am defining the function? F of m plus n root 2 is equal to m minus n root 2. This is the way I have defined it. So here my intention is it an isomorphism or not? The function what I have defined, is it an isomorphism or not? That is my intention to check. So you please take a note of the question, then we discuss the approach. So isomorphism is nothing but, under the definition of F, we have to verify that it is a homomorphism and it is a bijection, so that it will become the isomorphism. Agree? So please take a note of that. Right. Now, first we prove that it is a homomorphism. So let us take two elements first. You take x is equal to a plus b root 2, y is equal to c plus d root 2. So you consider f of x plus y. So it is nothing but f of adding the two values a plus c plus b plus d root 2. Now see how the function is defined. Whenever an element is of the form, this plus is replaced with minus. Remaining values are taken as it is. Applying the same definition here, it is nothing but a plus c minus b plus d root 2. Separating the terms, you can write it as a minus b root 2 plus c minus d root 2, nothing but f of x plus f of y. Please check. Do we accept for it? So first condition of homomorphism is satisfied here. Here if you want to prove that f is a homomorphism, it must satisfy two conditions. Now let us go with the second condition. How we take? If you consider f of xy, so you are simply multiplying these two. This is f of, if you multiply the values ac plus 2bd plus ad plus bc of root 2. So applying the definition of f here, it is ac plus 2bd minus ad plus bc root 2. Now what happens? I request you to calculate f of x dot f of y. It is nothing but a minus b root 2 into c minus d root 2. So if you multiply these two, you will get the same thing. Therefore, f of x equal to f of x dot f of y. So f satisfies the two conditions, hence it is a homomorphism. Okay? Please take a note of that and inform after noting. So to prove the second condition, I have calculated LHS and RHS separately, or you can simply split there. There from the very product you can write it as a minus b root 2 dot c minus d root 2 straight away, because we know that it will become the homomorphism. Otherwise, the second strategy is calculate LHS, RHS separately and check whether they both give the same value or not. That is the other idea, the general thing we do actually. If anybody has any questions, you can ask. Any questions, any doubts for anybody? Shall I proceed? Right. Now, if you want to check the onto property, so this is the domain z of root 2. Codomain is also the same set z of root 2. So to check for onto property, if you take any element on the right hand side, say I have taken, for example, say t plus q root 2. So what could be the domain value? It is very simple. You simply take it as p minus q root 2, because if you consider f of p minus q root 2, as per the definition, it is p plus q root 2. How it comes? Because this is nothing but f of p plus minus q root 2. So this plus is replaced with minus. So minus into minus, plus will come there. So for every element of this form here, you will get the corresponding thing in the domain, which is nothing but the pre-image. So from this you can say it is the onto property. And if you want to verify for 1 function, is f becomes 1 or not, so you take x is equal to a plus b root 2, y is equal to c plus d root 2 in z of root 2, such that f of x is equal to f of y. So what is the condition of 1, 1? Whenever images are equal, then corresponding elements must be equal. That we need to show. So I have taken that for these two elements, images are equal. So I have to check that x is equal to y or not. So from the very definition, it is a minus b root 2 is equal to c minus d root 2. If you compare the rational part as well as irrational part here, from this you can say a is equal to c and b is equal to d. Therefore, x is equal to a plus b root 2. This is equal to c plus d root 2 equal to y. So whenever images are equal, corresponding elements are also equal. Therefore, it is a 1, 1 function. So f is 1, 1 onto and homomorphism. Hence, it is an isomorphism. That is the solution of the problem. Please check that. Shall I proceed then? Any questions? Right. So earlier we have done a problem that I have taken r power c as all continuous functions from closed interval 0, 1 to r. So in r power c, I have taken m, that m is set of all functions for which 1 by 2 is a root. And in the previous problem, we have proved that m is generated by g, where g is equal to the linear polynomial x minus 1 by 2. So what my intention is, I want to show that this m is maximal ideal. Okay, this m is maximal ideal. That is my intention. So for this, the technique is I want to prove, or I want to use the fundamental theorem of homomorphism. Actually, we didn't prove, but as you know the statement, I just want to make use of the fundamental theorem here. So how I am going to use the fundamental theorem? Let us check. So let me say I want to define a function theta from r power c to r. So domain contains all functions, codomain contains real numbers. So how it is defined? Theta of any function g is equal to z of 1 by 2. In this way I have defined. So for every function in the domain, I am defining like this. Now, this theta will become onto and a homomorphism. So if I define the function like this, then the function is a homomorphism and onto also. So how I am going to prove it? So first of all, you take two functions. Let f comma g belongs to r power c. Consider theta of f plus g. As per the theta definition, it is nothing but f plus g at 1 by 2. So substituting the x value 1 by 2 here, it is f of 1 by 2 plus g of 1 by 2, nothing but theta of f plus theta of g. Because as per the addition of functions is considered, these two are equal. Addition of functions, these two are equal. Similarly, if you consider theta of fg, this is nothing but fg at 1 by 2, nothing but f of 1 by 2 into g of 1 by 2. So equals to theta of f into theta of g. So the two conditions of homomorphism is satisfied by the function theta. So theta is a homomorphism from r power c to r. You just take a note of this. If you have any queries, you can ask after noting. Right. Now, I have proved that theta is a homomorphism and I have to prove that it is onto also. How it is? See, the domain is having all functions. The codomain is having all real numbers. So for every element in the codomain, I have to take a function here. So let me say, if I take any real number r, what could be the corresponding pre-image, which is a function. So what kind of function I am considering in the domain? R power c contains all continuous functions from 0, 1 to r. So here I need to determine a function here. So very simple, if you say that h is the pre-image of r, how this function h is defined? You simply define it as a constant function. So what I mean, if you take the number 5, what is the corresponding function here? H of x is equal to 5. You define like this. So if you take the function as 9, number, the right side value. So how h is defined? You define it as 9. So you are defining h from closed interval 0, 1 to r as a constant function. So whatever the constant you take on the codomain, that corresponding constant function is defined like this. Since every constant function is continuous, this is a continuous function. So trivially it becomes onto. Okay? So the function theta is a homomorphism as well as onto. In this way, we will get the pre-image. So if you are particular, sorry, if you are particular that how it becomes onto, so theta of h, if you consider, it is nothing but h of 1 by 2. As per theta definition, this is nothing but r, because whatever the value you will take, h gives that value. You have defined h in such a manner. You can take 1 by 2, 1 by 4, 0, 1, anything in place of x here. H of x is always nothing but that number, as per the h definition is considered. So this is onto function. So we have proved that the function is a homomorphism and onto also. So up to this step, anybody has any doubts? Please tell me. Please tell me. Right. Now, here comes the beauty of fundamental theorem. As per fundamental theorem, domain by kernel is isomorphic to codomain. This is the beauty of fundamental theorem. Yes, h is onto. Why? Because, see, how theta is defined, theta from r power c to r by theta of any function is equal to the value of the image, right? So I am saying that now you take any real number on the codomain. You give me a number here on the codomain. You give me a number here. You give me a real number on the codomain. 4. Now, corresponding to 4, I should get a function here, right? What kind of function I should get here? So what is r power c? It contains only continuous functions defined from closure interval 0, 1 to r. So if I want to have a pre-image, I must know a function is there which gives the value 4 and it is continuous and it is defined from closure interval 0, 1 to r. So how I am defining the function? If you say that this is nothing but the function h, I am taking the function as from closure interval 0, 1 to r by h of x is equal to 4. You define like this. Whatever the number you take the function like this. This is a constant function, so it is continuous obviously, right? So if you consider theta of h, it is nothing but h of 1 by 2, nothing but 4. Therefore, it becomes onto. Clear now? Any questions for anybody? Therefore, as per fundamental theorem, domain by kernel isomorphic to codomain. Is it acceptable for all? Now let us calculate the kernel, what it is actually. So if you write kernel, this is the definition of kernel. I am taking the functions in the domain such that the image is 0. So this is nothing but set of all functions such that f of 1 by 2 equal to 0. And this is nothing but m. This is m actually in the problem. So kernel is m. Clear now? So here we can say that r power c by m is isomorphic to r. Clear? Any questions you can ask? Please tell. Any questions for anybody? Now see, what is the significance of isomorphism? Whenever you say that two sets are isomorphic, whatever the structure, pattern, properties are satisfied by one set, the same thing will be satisfied by the other. It is a ring, it is also a ring. It is commutative, it is also commutative. It has unity element, it also has unit element because they are isomorphic. They are very similar, right? And what is R? This is the real number system. So you have the the set of number system, integers, rational numbers, real numbers, complex numbers. Among these things, Q or C, these are nothing but fields. Accepted? You know this? Yes or no? Rational numbers, real numbers, and complex numbers are fields. So this is a field. Since these two are isomorphic, it also a field. So R power C by M is a field. Now see, here comes the previous class result. R by I is a field if and only if I is maximal. Can you recollect the previous class problem? Very lengthy proof we have done in the previous class. Can you recollect this? So, since it is a field, from that very result, M is maximal. Now you can understand the impact of previous results, fundamental theorem, and isomorphism here. We have implemented three things. We use the technique of fundamental theorem. We use the technique of previous result. See? So, there is no direct proof that M is maximal ideal. You can try for it, but the proof is somewhat lengthy. But this is very easy. By simply having a homomorphism between these two, applying fundamental theorem, the proof gets completed. You have proved that it is maximal. So it is also a previous year question. So these two things are given the previous year papers. You can check for that. It is a maximal ideal. Okay. So since we have started after the vacation, I just want to take or give a break for you for this today's session. Tomorrow we will continue as usual, right? So you come up with these things for tomorrow's class and we will discuss new things with regard to homomorphism and as well as ideals. Okay. So that's all for today. Thank you very much.